This is module 6 of chapter 2. In this module, we have discussed about the inverse interpolation methods. In previous modules, we have discussed several interpolation methods, and all these methods are used to find the value of y for a given values of x from a table of values of x and y. But the inverse interpolation is different. In inverse interpolation, we have to determine the value of x for a given values of y from a table of values of x and y. That means we have to determine the values of independent variable for the given values of the dependent variable y. A very few number of inverse interpolation methods are available in literature. In this module, we shall discuss about 3 inverse interpolation methods. First, we consider the inverse interpolation method based on Lagrange formula. The Lagrange interpolation formula of y on x is y equal to summation I equal to 0 to n wx into yi whole divided by x minus xi whole into w dash at xi. So, from this formula, a polynomial in x is obtained, and hence one can determine the value of y for a given values of x. Now, we interchange x and y in the above formula, and we obtain the following formula. That means, we get the value of x which is equal to summation I equal to 0 to n wy into xi whole divided by y minus yi into w dash at xi, and which can be written as summation I equal to 0 to n li yi into xi, where y is called the Lagrangian function on y. The explicit form of li y equal to y minus y0 into y minus y1 up to y minus yi minus 1 into y minus yi plus 1 up to y minus yn whole divided by yi minus y0 up to yi minus yi minus 1 into yi minus yi plus 1 up to yi minus yn, and wy equal to y minus y0 up to y minus yn. So, it is easy to observe that this formula gives the value of x when the value of y is given. This formula is known as Lagrange inverse interpolation formula. The concept of this formula is simple, but practically this formula needs more arithmetic computation. So, this formula is not suitable for hand calculation, but it can be easily programmed for the computer users. This formula is illustrated with the help of an example. In the following table, the time and the corresponding velocity v of a particle moving with non-uniform velocity is given, and from this table we have to determine the time when the velocity of the particle becomes 2.75. So, for this case, the value of the variable v equal to 2.75, this is the value of the dependent variables, and the appropriate formula for this case is the time t equal to L0v into T0 plus L1v into T1 plus L2v into T2 plus L3v into T3, where the first Lagrangian function L0v is equal to v minus v1 into v minus v2 into v minus v3 whole divided by v0 minus v1 into v0 minus v2 into v0 minus v3. And after substituting the values of v0, v1, v2 and v3, the entire expression is equal to 0.64801. Similarly, L1v is equal to 0.75601 and L2v is equal to minus 0.56920 and L3v is equal to v minus v0 into v minus v1 into v minus v2 whole divided by v3 minus v0, v3 minus v1 into v3 minus v2. After simplification, we get the value of L3v equal to 0.16518. Thus, the required value of t, the time t is 0.64801 into 0, this is the value of t0, plus 0.75601 into 1, 1 is the value of t1, minus 0.56920 into 1.5, 1.5 is the value of t2, plus 0.16518 into 2, 2 is the value of t3. After simplification, this becomes 0.23257. So, this is the value of t when the velocity of the particle v is equal to 2.75. Now, we come to another inverse interpolation formula based on Newton's forward difference interpolation formula, but this formula is not the direct method, this is an iterative method. We know the Newton's forward difference interpolation formula as y equal to y0 plus u into delta y0 plus u into u minus 1 by factorial 2 into delta 2 y0 and so on, where the new variable u is equal to x minus x0 by h. From the second term of the right hand side, the above formula can be written as u equal to 1 by delta y0 square bracket start y minus y0 minus u into u minus 1 by factorial 2 into delta 2 y0 and so on. The last term is minus into u minus 1 into u minus 2 up to u minus n plus 1 into delta n y0 whole divided by factorial n and square bracket closed. Note that the value of u depends on the value of u. So, it is not possible to find out the value of u without the initial or starting value of u. The first approximate value of u is denoted by u1. By neglecting the second and higher differences, we obtain the first approximate value of u as u1 equal to 1 by delta y0 into y minus y0. Similarly, the second approximate value of u, that one is denoted by u2, is obtained by neglecting third and higher order differences. That means, the value of u2 is equal to 1 by delta y0 whole into y minus y0 minus u1, that means the first approximate value of u into u1 minus 1 whole divided by factorial 2 into delta 2 y0. So, this expression gives the second approximate value of u and this is denoted by u2. Similarly, the third approximate value of u, that one is denoted by u3, is given by this expression. In general, the k plus 1th iterated value or k plus 1 approximate value of u is obtained from the following formula. That means u k plus 1 equal to 1 minus delta y0 square bracket start y minus y0 minus uk means the value of u at kth iterated value or kth approximate value into uk minus 1 by factorial 2 into delta 2 y0 and so on. And note that all the values of k plus 1 iteration is depends on the value of u of kth iteration or the kth approximate value. And for this expression, the values of k are 0, 1, 2 and so on. Now, this process is repeated until two successive approximation, that means the value of u at k plus 1 iteration and the value of u at kth iteration be equal to up to a desired number of significant figures. That means the absolute value of u k plus 1 minus u k is less than epsilon, where epsilon is a very small positive pre-assigned number. Once the value of u is obtained by iteration method, then from the equation x equal to x0 plus u k plus 1 into h, that means this expression x0 plus the k plus 1 approximate value of u into h gives the final value of x. Now, this iteration method is illustrated by this example. So, based on the following table, we have to determine the value of x when y equal to 4.8. So, the previous methods, that means the approximate method or Newton iteration method is used to find the value of x when y equal to 4.8. Now, for the given table of values, we have constructed the forward difference table as follows. The first column represents the value of x, second column is the value of y, third, fourth and fifth column are the values of first difference, second difference and third differences. The red marked values are used in the formula. So, in this problem x0 equal to 3.0 and the step length h equal to 0.5. Now, we use the successive approximation method to find the value of u. The first approximate value of u, that means u1 is 1 by delta y0 into y minus y0 equal to 1 by 1.5014. This is the value of delta y0 whole into 3.2 minus 4.6231. After simplification, this expression is equal to 0.1178. That means this is the value of u at the first iteration. Now, the second approximate value of u, that means u2 is equal to 1 by delta y0 into y minus y0 minus u1 into u1 minus 1 by factorial 2 into delta 2 y0, which is equal to 0.1178 minus 0.1178 whole into 0.1178 minus 1 by 2 into minus 0.1937 whole divided by 1.5014. After simplification, the value of u2 is equal to 0.1111. Similarly, the third approximate value of u is equal to 0.1160. So, we have obtained three approximate value of u, that means u1, u2 and u3. Using these values, lastly we can conclude that the approximate value of u is 0.1160. Thus, the value of x when y equal to 4.8 is given by x equal to x0 plus u3 into h, which is equal to 3.0 plus 0.1160 into 0.5, and after simplification the value of x is equal to 3.058. Thus, the value of x is 3.058 when y equal to 4.8. Based on the Newton's backward difference interpolation formula, we have derived another inverse iteration formula. The Newton backward interpolation formula is y equal to yn plus v nabla yn plus v into v plus 1 by factorial 2 into nabla 2 yn and so on, where v equal to x minus xn by h or x equal to xn plus vh. The value of the variable v can be obtained as v equal to 1 by nabla yn into y minus yn minus v into v plus 1 by factorial 2 into nabla 2 yn and so on. The last term is minus v into v plus 1 up to v plus n minus 1 whole divided by factorial n into nabla n yn. So, the value of v is obtained from the second term of the right hand side of the Newton's backward interpolation formula. The first approximate value of v is obtained by neglecting second and higher order differences, and that means the value of v1, that means the first approximate value of v is equal to 1 by nabla yn into y minus yn. The second approximate value of v, that one is denoted by v2, which is equal to 1 by nabla yn into y minus yn minus v1 into v1 plus 1 by factorial 2 into nabla 2 yn. Similarly, the third approximate value of v is denoted by v3, which is equal to 1 by nabla yn into y minus yn minus v2 into v2 plus 1 by factorial 2 into nabla 2 yn minus v2 into v2 plus 1 into v2 plus 2 whole divided by factorial 3 into nabla 3 yn. In general, the k plus 1 approximate value of v, which is denoted by v k plus 1, is equal to 1 by nabla yn into y minus yn minus vk k plus 1 whole divided by factorial 2 into nabla 2 yn, and the last term is vk plus 1 up to vk plus k whole divided by factorial k plus 1 into nabla k plus 1 yn, and this formula is valid for all k equal to 0, 1, 2 and so on. This iteration process repeats until two consecutive values of v becomes equal up to a desired number of significant figures. Finally, the value of x is determined from the equation x equal to xn plus v k plus 1 into h. So, using this formula we can finally obtain the value of the unknown variable x for a given values of y. So, we have discussed three inverse interpolation methods. One is called Lagrange inverse interpolation method, and other two are the iteration methods based on Newton's backward and forward interpolation methods. The inverse interpolation methods can be used to solve many other problems. Here we discuss inverse interpolation method to find a root of an algebraic and transcendental equations. The algebraic and transcendental equations appears in many problems in science and engineering. Now we discuss inverse interpolation method to find a root of an equation. The equation may be an algebraic equation or it may be a transcendental equation. Let f(x) equal to 0 be an equation and one of the roots, say xi, lies between a and b. That is f xi equal to 0 and a less than xi less than b. To find the root by inverse interpolation method, a table is to be constructed for some values of x between a and b. The first row of the table contains the values of x and second row contains the value of y, which is equal to f(x). Now, if we use Lagrange interpolation method, then the arguments, that means the values of x, may or may not be equal spaced, but for Newton's method the argument must be equal spaced. Now, our problem is to find the value of x such that y equal to 0 and the value obtained by the iteration method, inverse iteration method or inverse formula based on Lagrange interpolation methods. The value of x is the desired root of the given equation. Now, the method is illustrated by considering an example. Here we consider an equation x cube minus 2x square plus 0.5 equal to 0. Our problem is to find a root of this equation by inverse interpolation method. Let y equal to f(x), that means the given equation, which is equal to x cube minus 2x square plus 0.5, and it is easy to verify that the one root of the equation lies between half and 3/4. So, for inverse interpolation we have to construct a table, and for this purpose we consider 6 values of x within this interval, and the values of x are taken as 0.50, 0.55, 0.60, 0.65, 0.70 and 0.75, and then we construct the following table. X and y, first row contains the values of x and second row contains the value of y. The value of y is calculated from the expression x cube minus 2x square plus 0.5. So, for this table of values we constructed a forward difference table, or we can say this is a backward difference table. The first column of this table contains the value of x, second column contains the values of y, third, fourth and fifth column contains the values of first difference, second difference and third differences. Since our problem is to find the root of the given equation, so for this problem the value of y is 0 and we have to calculate the value of x. The first approximate value of u, that means u1 is equal to minus y0 by delta y0. In this case y equal to 0, that so the formula for u1 is simplified as minus y0 by delta y0, and by substituting the values of y0 and delta y0, the value of u1 is finally 1.964636, and the second approximate value of u, that means u2 is equal to 1.938573. The third approximate value of u3 is equal to 1.939394. That means the third approximate value of u is taken as 1.939394, correct up to 6 decimal places. So, using these values we have the value of x as x0 plus u3 into h, which is equal to 0.50 plus 1.939394 into 0.05, because the value of h is 0.05. After simplification it is equal to 0.596970. So, this value, that means 0.596970 is the root of the given equation, correct up to 6 decimal places. Let f(x) be a function which is equal to 1 by 1 plus x square, and it is defined on the closed interval minus 3, 3. So, for this function the second degree interpolating polynomial is y equal to phi 2x equal to 1 minus 0.1 into x square. This is the second degree approximate polynomial for the function fx. And the fourth degree polynomial, interpolating polynomial, is y equal to phi 4x. Phi 4x is actually the fourth degree polynomial corresponding to the given function fx, and this is equal to 0.15577 u4 minus 1.24616 u to the power 3 plus 2.8904 u to the power 2 minus 1.59232 u plus 0.1, where u equal to x plus 3 whole divided by 1.5. The curve of y equal to fx, y equal to phi 2x and y equal to phi 4x are shown in the next slide. In this diagram, the blue line or blue curve represents the function fx. The red curve, that means the parabolic curve, represents the second degree polynomial phi 2x, and the green curve represents the fourth degree polynomial phi 4x. Note that the value of fx and phi 2x are positive, that means the upper half of the x axis, but the value of the polynomial phi 4x is negative for certain values of x. So, for this function, the fourth degree polynomial gives some negative values for some values of x. That means it is negative when x equal to 2, but the exact value is positive. So, at this point, that means when x equal to 2, the value of f is 0.2, phi to 2 equal to 0.6, that means the error between the exact value and the approximate value obtained by second degree polynomial is 0.4, but the value obtained from fourth degree polynomial, the value is minus 0.01539, the negative value, but the error is 0.195. It may be noted that the functions y equal to fx and y equal to phi 2x are positive all values of x, and it is very natural, but the value of y equal to phi 4x is negative for some values of x. Now, we shall discuss about some methods or some choices of interpolation formulas which are discussed in previous modules based on the given table of values. If the arguments are not equally spaced, then Lagrange, Newton's divided difference or Atkins iteration formula may be used. All this formula needs more computation time than Newton's forward and backward interpolation formula, but the Newton's forward and backward formulas are applicable only when the arguments are equally spaced. This is the one limitation of Newton's formula. The Newton's formula is used when the interpolating points is at the beginning of the table, whereas the Newton's backward formula is used when such point is at the end of the table. Another interpolation formulas are also derived in previous modules. These are Stirling and Bessel formula, and these are called the central difference interpolation formula, and these formulas are useful when the interpolating point is at the center of the table. It can be verified that the Stirling formula gives more accurate result or more better result when the values of x lies between minus 1 by 4 and 1 by 4. The Bessel formula gives better result near s equal to half. That means if s lies between 1 by 4 and 3 by 4. If all the terms of the formula are considered, then all the interpolating formulas gives same results, including the Bessel formula and Stirling formula. In this module, we have discussed three inverse interpolation methods. One is Lagrange interpolation method, and other two are iterative inverse interpolation methods based on Newton's forward and backward interpolation formula. The inverse interpolation method is also used to find a root of an algebraic or transcendental equations, but it is seen that this method is not suitable to find a root of an equation, but we have discussed many suitable or very good methods to find a root of an algebraic or transcendental equation in chapter 4. Also, we have discussed the choice of interpolation formula based on the given table of values.